The next thing I want to do is exercise 4.30, which I think is one of the coolest exercises. And I just want to do it in detail for everybody. I think it's too important to leave it as an exercise for you. So what I want to do is I want to integrate. This is now just a normal Calc 1 integral. From 0 to 2 pi, 1 over 2 plus sine theta d theta. Now, I say this is a Calc 1 integral. It is not a Calc 1 integral. There are no methods in Calc 1 that can solve this. There are no methods in Calc 2 that can solve this. It turns out you actually need complex analysis to solve this. And that's a little bit surprising because there's nothing about complex numbers that appears here. We're talking about the sine function, which is here just defined as theta ranges over the real numbers from 0 to 2 pi. And everything's fine. Nothing here seems imaginary, and yet we need the methods of complex analysis to evaluate this integral completely. And so I want to explain how this works and show you how we could do this. Now, the first thing I want to do is I want to recognize sine of theta as a sum of exponential functions. So here we're introducing kind of artificially sine of theta written as a sum of exponential functions. So this is going to be sine of theta is going to be e to the I theta minus e to the negative I theta all over 2I. And we're still integrating with respect to theta. Now I just want to manipulate this just a little bit. We have a fraction within a fraction. So here I'm going to multiply the top and bottom by 2I. So this is going to be equal to 2I over, let's see, if I multiply the bottom by 2I, the 2I over here goes away. So this will be e to the I theta minus e to the minus I theta. And if we multiply the 2 by 2I, we'll get 4I. Okay, so that's e to the I theta minus e to the minus I theta. And then the last thing I want to do is I'm going to multiply by e to the I theta over e to the I theta. The reasons for that will be apparent shortly. But this is going to give us the integral of 2I e to the I theta all over, and let's see, if I multiply through the parentheses by e to the I theta, we're going to end up with 4I e to the I theta times e to the 2I theta minus 1 d theta. And in fact, just to be a slight pain, I apologize, I'm going to move this I e to the I theta outside. Hopefully you'll see what's going to happen next. And these are still, I just forgot the integrands, or the bounds for the integral. I mean, this is still from 0 to 2 pi. Now what I'm going to do is I'm going to deconvert this from an integral like this into a complex integral. So into a non-parameterized integral. So if you let z be e to the I theta, then this would be the integral from, let's see, we're going to integrate over gamma. We're going to have a 2 up top. Notice that, so really what I'm thinking of here is I'm thinking of kind of going backwards from, you have the integral of f of z dz over gamma, where gamma of t is e to the it, as t goes from 0 to 2 pi. So we're used to going from an integral in terms of z to an integral in terms of theta, or in terms of t. Here we're going to go backwards. We're going to go from theta to z. So we're going to just do this slightly backwards, or slightly, backwards from what we're used to. But our e to the I theta, we're going to think of as z. So this is going to be z squared plus 4z plus 4iz. I forgot the I. 4iz minus 1. And that's a 2 up top, not a z in the numerator here. This is a 2. Now the I that used to be in the numerator got moved over here. And the reason why I put this here is that if z is e to the I theta, then dz is I e to the I theta d theta. So in other words, think about going in the other direction. When you evaluate this integral, you always compute f of gamma times gamma prime. This is the, this is the gamma prime that we need to undo. So hopefully that makes sense where you see all those pieces, where all those pieces go. And then this is the integral of 2 over z squared plus 4iz minus I. And again, we're integrating over gamma, where gamma is this integral here. Okay, so here I'm just going to copy this down. Gamma is e to the it as t goes from 0 to 2 pi. Or e to the I theta, whatever. I'm confusing t's and thetas, but it doesn't matter what variable we use. Now we need to figure out how do we evaluate this integral. So what we're going to do is we're going to figure out first, is the denominator ever 0 inside the circle of radius 1? So if I take a circle here, so here's our Cartesian plane. I'm going to take a circle of radius 1, okay, centered at the origin, because that's what this curve represents. And I want to think about, is our function ever going to be 0 inside that circle? And if yes, then we'll have to work very carefully. If no, then the integral is 0, and we're done. So we have to figure out when is the denominator equal to 0. So we're going to have z squared plus 4iz minus I equals 0. And to solve this, what we're going to have to do is just apply the quadratic equation, or if you like, you can complete the square. Again, I just like completing the square. I don't have a good reason for it. And it turns out that completing the square over the complex numbers works the same as completing the square over the reals. So you're going to take half, you're going to take half of the linear term and square it. So it's 2i. 2i quantity squared will be 4i squared, or minus 4. So I'm going to subtract 3 from both sides. And again, the reason for that is that this is going to make it so that the left-hand side is a square. So this is going to be z plus 2i squared is equal to negative 3. And therefore, z plus 2i is equal to plus or minus square root of 3i. And therefore, z is negative 2i plus or minus the square root of 3i. All right, and then really all we had to look at is to determine whether or not any of these values fall within the circle of radius 1, centered at the origin. And unfortunately, they do. So if you think about the negative term, z is negative 2i minus square root of 3i. So square root of 3 is like 1.5. It's somewhere between 1 and 2. It doesn't matter where. This would be something like negative 2 plus square root of 3i. And that's definitely outside of that circle. Okay, so this square root of 3 is again something like 1.5. So this is going to be something like negative 3.5i, which is going to be way outside of the circle here. So at this point, we don't have to worry about it all. But we have another solution. We have negative 2i plus square root of 3i. And so I'm going to write that as square root of 3 minus 2i. And again, square root of 3 is something like 1.5. So if we take 1.5 minus 2, that's going to be about negative 1/2 I. And unfortunately, that is inside that circle of radius 1. So we're going to have to deal with this one separately. Okay, so we'll just have to deal with that separately. So now that we know that one of these is inside that circle and one of them is not, what we're going to do is I'm going to take this integrand, this 2 over z squared plus 4iz minus 1 quantity. That's what we're going to have to look at. So z squared, let me write it the way that I have it up here, z squared plus 4iz minus 1. And what I'm going to do is I'm going to factor the denominator. And we can do that because we know when the denominator is 0. And I'm going to need just a little bit more room here. So let me save myself some trouble later. Squeeze a little bit more here. So it turns out that this is going to be, and the top stays the same. I don't care about the top. But this is going to be 2 over z minus one of the terms. So let's say z minus this term. So negative quantity 2 plus square root of 3i times z minus the other term, minus the quantity square root of 3 minus 2i dz. Okay. And so I'm going to think of this as, this is all over gamma. I'm going to think of this as this part, 2 over z minus the first root that's outside the circle. So it's going to be 2 over this, the minus is canceled. This is z plus the quantity 2 plus square root of 3i, all over the other term, z minus square root of 3 minus 2i dz. And now if you look at this carefully, notice that the numerator is a function that's holomorphic over the region gamma, and gamma is nice and has all the properties that we want from Cauchy's integral formula. It's piecewise smooth, closed, positively oriented, and simple. The value w that we're looking at is square root of 3 minus 2 times I, because it's always z minus w. So here, our w is square root of 3 minus 2 times I, okay, which, like we said before, was one of the solutions. And our f of z is the numerator. It's the 2 over z plus 2 plus square root of 3 times I. And so it turns out that this integral is going to be equal to 2 pi I f of w, right, by Cauchy's integral formula. And that's going to be 2 pi, let's just wall this off here. So it's going to be equal to 2 pi I times, let's see, what's f of w? Well, that's going to be 2 over, let's see, square root of 3 minus 2i plus 2 plus square root of 3i. And so the 2 i's cancel. And you're going to end up with square root of 3i over square root of 3i. And you end up with, let's see, the 2's cancel, the i's cancel, and you end up with 2 pi over square root of 3. And so it turns out this is exactly what this integral is. The integral from 0 to 2 pi of 1 over 2 plus sine theta d theta is equal to 2 pi over square root of 3. And when you write it as the start and stop of the problem, when you write it as the initial problem and the answer, and you don't see the method, it's not obvious that complex analysis played any role whatsoever, but it definitely did. In fact, Cauchy's integral formula played a role. Okay, so I thought that this was cool enough. I wanted to actually write out all the details and show it. And there we go. So what I would suggest that you do for an exercise is try to evaluate the integral from 0 to 2 pi over, so 1 over 2 plus cosine theta d theta. See what happens. Try that on your own. Let me know how it goes.